Alrighty. Thank you guys for coming out. I know it's getting late, right? Sunday afternoon, so I appreciate you being here. Today is going to be an introduction to RF demodulation. So this is going from 0 to 1 and learning how to take energy out of the air and turn it back into the original bit stream that was sent by the transmitter. And so the natural follow-on to this is transmission, but if you don't understand the principles behind how it works in the first place, we can't really get there. So I think it's important to start with the demod, and you can do this for pretty cheap, and ideally after the end of this hour, you guys should have a good understanding of how to get started. So a couple reasons why we're here. This really isn't that hard. Unfortunately, there is not a lot of step-by-step guides to doing this online. There's a lot of information out there, but if you don't want to sit through a 4-month university course, it's hard to get the A to Z on this stuff. And so I hate school. I think a lot of other people here are not the fondest of formal education, and so I want to give you an abbreviated version of that 4-month course in about an hour, right? And so we're not going to cover everything. We're going to get a very brief primer in theory, but it'll be enough to understand what we're doing. And so with this knowledge, you can do a lot of really cool things. You can, for example, there was somebody in LA that was decoding just arbitrary energy and found the FBI surveillance planes that are flying around intercepting phone calls. And they were using some of the stuff from the NSA playset, allegedly, we think. But the idea is that there's all sorts of energy out in the air, and with these kinds of skills, you can go and start to investigate that stuff and understand what's happening in the world around us. And I want you to be able to do this kind of stuff too, right? I want to make some friends who are also interested in this stuff so that we can work on these things together. And I think there's a lot of like-minded people, especially at this conference, that would be interested in this kind of stuff. So with that said, who am I? Just a brief thing on me. Security guy. I do a lot of different things, and I have done a lot of different things over the years. I started in defense, and then doing a lot of embedded work. I eventually moved more towards the cloud and web side, which is what I'm doing today. Worked at a self-driving car startup for a little bit, and today I'm with Airbnb on the enterprise security side. And I like doing off-roading and all sorts of stuff outdoors. If you guys are into that kind of thing, please see me afterwards. We have a couple groups that go out quite a bit. So, high level for today. We're going to start with some theory. I promise I'm not going to kill you with this. It'll be 5-10 minutes max, but it's enough that we can understand everything else going on. And then we'll go through the steps required to do this. So the first is carrier identification, where we're going to find the source of the power wave that's being used to transmit that data. Then we're going to capture that energy and store it on our hard drive. We're going to inspect it, and then eventually get the data back out and decode it into the original data. And how are we going to do this? I spent way too much money, and now I have 80 automotive key fobs in a bag up here. And if you would like to grab one of them after to do this yourself, I'm happy to give them away. I've got all sorts of stuff. I've got some Benz key fobs. I think I've got a couple Toyotas in there, Kia, some other stuff. And they're all different things. So we're going to talk about different types of modulation today. Different key fobs have different types of modulation. And some of them have multiple different types, depending on what kinds of actions you're doing. So if you want to grab a couple and play with them, you're definitely welcome to do that. I would like to get rid of them all, so please come up and see me. OK, cool. So let's get started with some theory. Again, I'm not going to kill you with this, but it is important. So the principal concept here that we need to understand is the idea of modulation. So this is taking data, or a signal. In this case, we have this analog wave, this message signal at the top. And then we have a power wave. This is called our carrier signal. And we're going to use our modulation to take that data and modulate it onto the carrier to get our final wave that we're going to transmit using our radio. And so here you can see we have our analog wave that gets reflected over that axis. And using the carrier signal, we transmit that data, right? So we need both components. And modulation's kind of interesting. So for a lot of weapon systems, you don't actually need modulation. A lot of this is a show on Netflix right now called Three Body Problem. It's a sci-fi show. I really enjoyed it. And this is one thing they got right. So there's this quote, frequency modulation is not necessary for weapon systems. And the reason why this is the case is that a lot of weapon systems just take a massive amount of energy and transmit it at a target. And the idea is to overwhelm the receiver so that they can't figure out what that data was that was modulated in the first place. Imagine somebody's trying to talk to you and everybody else is screaming in the room. You're not going to be able to understand the data that was being transmitted, right? And so this does require a carry signal, and modulation is required for data. When I, previous years, was in Afghanistan in the Middle East, we had these giant antennas on our vehicle. So you can see on the passenger side front there, that antenna can do about 1,000 watts of energy. And the idea is that if you're patrolling and you are trying to interfere with improvised explosives, right? And so somebody's on a cell phone, they're trying to call in, and you transmit a massive amount of energy, the signal is not going to get to that receiver. It's not going to understand the call came in, and theoretically the bomb's not going to go off, right? And this is the whole idea of modulation and when you do or do not need it, right? And so this is very effective. This is still in use today. It's a common technique for interference. And so let's talk about some simple radio waves. So the two common types of analog waves are FM and AM, and I'm sure we're all somewhat familiar with this for our car radios, right? Like if you have AM stations, you have FM stations, and specifically the difference is that with AM, we're changing the power level of the wave to transmit the data. With a FM signal, we're modulating the frequency, so we're changing or modulating the frequency. And there are different cases where this is valuable. So AM waves are generally slightly more efficient. So given the same amount of energy, we can transmit that wave a little bit farther. However, it's more prone to interference. So same thing as we were talking about previously, somebody screaming in the room next to you. With an AM signal, we're reliant on the level of that signal, right? So how loud it is to figure out what the data was. And so if you have a bunch of noise from, let's say, power lines or Wi-Fi antennas or Bluetooth transceivers or things like that, depending on the frequency you're at, this can be a real problem. And so with FM, we don't change the power level, which means we can forget about all that interference. Instead, we're just changing the frequency. And the important thing here is we have a carrier wave that we're using as a reference point. So the carrier wave would either be, let's say it's 10 decibels for an AM signal, and we modulate the difference off of that, right, to figure out our data. Or with FM, we could say, in the case of our key fobs that we're going to be using later, we have a signal at 433 megahertz, and the difference between that carrier wave and whatever we're receiving is the data, right? So it's harder to interfere with that because it's frequency modulated, not the power. And so that's the principle. This is going to probably be the most important slide in terms of understanding what we're doing later. And so this is analog, right? But we're talking about bit streams, and bit streams are digital. And so how do we modulate digital data? Well, we take these same concepts, so AM and FM, and we instead use shift keying, so amplitude shift keying or frequency shift keying. And so here you can see with a bit, right, a bit of 1, an ASK signal, amplitude shift keyed, we're going to have a presence of energy. And with a 0, we're going to have either no energy or a small amount of energy, depending on the type of ASK. For FSK, it's a frequency modulation. So we're going to change the rate of the wave, and that'll be detected by the receiver. The last one is phase shift keying, and I'm just going to anecdotally mention this. We're not going to do this today. But most Wi-Fi and other things today are done with some form of PSK, which is where we invert the wave. So anytime we have an inversion, let's say we have a sine wave, we invert it, now it's cosine, we're going to have a change in state here, and you can kind of see that. It might be a little bit small for you guys. Anytime we have an inversion, that represents a state change, right? And so for ASK, specifically we're going to focus on ASK and the simplest form of ASK today, which is on-off keying. Again, either the presence of energy or not. But there's other types of ASK as well. We have ternary ASK where we have different power levels to represent different amounts of data. And this allows us to do higher data rates because we have more states we can represent for each position, right? And quadrature AM is actually something that's used quite commonly today, where we combine changes in phase and changes in amplitude. And doing that allows it to transmit a little bit more data, but with more reliability. And so there are a lot of different types of modulation used in different scenarios, but Wi-Fi is probably the biggest example of modified QAM, for example. So step 1, that's all the theory. I promised it would be fairly painless. So now with some carrier identification, we're going to be able to get the process started of getting energy from the air back to data. And for a lot of devices, you can find this information online because there's an FCC requirement to publish this if you want to sell the device commercially. And especially for key fobs, this is very common. So again, our first goal here is to find the carrier wave because we need a reference point to analyze the data, right? And so we have two options. We have the shitty government version on the left, or we have a community-sponsored version, something that's put together to amalgamate all of those government databases into a single site. And this is called fcc.report. You can look it up on your computers. And there's fcc.gov if you want to do it the native way. But essentially what we're doing is we're taking an FCC ID, or you can use other search parameters like the manufacturer, things like that. And we're trying to figure out what the device is and find the FCC report for it. And so there is a lot of awesome information here. You can find user manuals. They're required to take pictures of the outside of the device, of course, but also internally. So you can sometimes get some board pictures, which can be helpful. And so this is our first example. I have this key fob in the bag if you guys want to check it out after. It is a Kia key fob from 2009, and it has this beautiful yellow sticker on it that gives us the FCC ID as a starting point. One second. And so this is what we need for our starting point. We have our FCC ID up at the top, PINHA T036. And we can use fcc.report to look this up. You'll see using the test report on the left, we find a carrier wave at 315 megahertz. That might be a little bit small, but that's the red box here. And so these test reports have all sorts of information in them. You'll see for some other ones, all right, this one is a BMW key fob. I have a few of these actually, so you can see a few different versions. You have the carrier wave is actually printed directly on the device. It just says 315 megahertz right on it. There's also an FCC ID printed here. And if you look this up, in the test report, they tell you the total bandwidth. So they tell you can expect this energy to be at 315 plus or minus 0.25%. And that's the modulation that we're seeing. I forget if this one's FSK or ASK, but that's the idea. And then the last one, this is the one that we're going to be looking at today. This is actually my Jeep. It is a 2021 Jeep Wrangler. And so this is a modern vehicle. This is still the key fob that they use on the Jeeps being released today that are coming off the lot as we speak. And it has been used since 2017 or so. And this test report is awesome. We actually get specific measurements off a spectrometer, or a spectrum analyzer, excuse me. And so you can see here, this is going to be too small to see for the folks that are in the audience here, but we have 433 and then a decibel rating, and then we also have sort of sidebands and other things available here just as additional data. But the most important part is that we get that carrier, because that's going to give us a starting point that we can use for later steps. And I want to show you examples of some of the other stuff. So again, like I said, you can get internal pictures a lot of the time. Sometimes you can even get block diagrams and schematics. It's very unusual, but I've seen it a couple of times. And so you can get in there and start doing, like for example, we'll talk about this later. You can hook up a clock to some of these radios and synchronize essentially like the electronic levels that you're reading off the board, off the chips, with the waves that you're seeing presently in the air. And if you have schematics, that's obviously very helpful. And so with that said, I want to talk quickly about hardware before we get into the demos. So I told you could do this for very cheap. Everything I'm doing today, everything in this talk, you could do with a $30 RTL SDR. This is an awesome device, very, very supportive community, both on Reddit and in other forums. And you can go on Amazon and buy this for $30 right now. The device we're going to be using today is, so the limitation of the RTL SDR is it only does receive. So if you guys want to be testing transmit eventually, you're not going to be able to do it with the RTL, unfortunately. You're going to have to move up to something like a Hacker F, which is what we're going to be using today. Looks like this. Standard ports for antennas and things like that. You have a clock input connected over USB. And the gentleman who runs, or who built this and supports it, his name is Michael Osman. He's got a lot of awesome guides on his website for this device as well. And again, there's a big community. It is more expensive at $350, but this gives us the ability to transmit. We get a slightly better sample rate, so higher definition, and we'll talk about that later. And we have enhanced bandwidth. So this device can do about 1 megahertz all the way up to 6 gigahertz, which, depending on what you're doing, can be important. And then the last thing, this is called a USRP. I would define this as more of a commercial option. It starts around $3,000, and depending on the model, goes up to about $4,000. This has much more bandwidth, and the most important thing about this is that it can do transmit and receive at the same time. So with the Hacker F, you can only do them independently. So you can either receive or you can transmit, but you can't do them simultaneously. And so you can imagine there are certain applications where you're interacting with a transceiver, and you need to be able to receive without resetting the radio, right? Cool. So I'm going to try to live demo this, and we'll see how it goes. And if that doesn't work, then I have backup videos. But let's give it a shot. All right, so I'm going to, plain Ubuntu VM here. Give me one sec. All right, yeah, so I'm going to native just plain out of the box Ubuntu VM, and I'm going to open a tool called GQRX, which is a digital spectrum analyzer, and it can use any SDR that we plug in. And you can actually just listen to FM radio with this. It has a radio modulator here. You can just select it here, put the channel in, and figure it out. In this case, our radio is at this frequency. I'll show you how this gets typed in. So you can just click on the box, right? And it's going to be 433. 936 for this key fob right here. I'm going to mute the output because this would just play for you what you're getting out of the air. And then I can start it, and you'll see we get a waterfall chart. And so this is all of the energy around me right now being received by this radio right here. And you can see we don't have much. There's nothing really happening that seems to be of interest. We have a couple interesting peaks, one at 432, something around like 437.5, and then obviously this one right here, right, at like 434.8 maybe. But you'll see it's going to be very obvious when I press the key. So I'm going to press the lock key, and we get some data, right? And so this is the first part. We're just verifying, right? As I get closer to the antenna, it's going to kind of overload things, right? You're seeing the sidebands out to the side there. But if I'm kind of far away, like this is verified, right? We know that we have a carrier wave at the FCC reported frequency of about 433.9 megahertz. And so from this portion, we can then go and capture that signal, and that's what we'll do next. Cool. So far, so good. All right, so next up, we verify that we have the carrier wave, and we see it at the frequency we anticipated seeing it at. And so our goal here is to now take that energy out of the air and save it to our hard drive. This is just going to be a binary blob. You can think of this as like an audio recording. So if I had this microphone, for example, right, they're recording this in the back, they're going to have captures of this mic, whether it's diaphragm mic or whatever. We're doing the same thing, but with an antenna and a demodulator, right? Or an antenna and just a receiver here. And so we're going to take that energy, and just like we're recording it with a microphone, we're going to save it to our hard drive. And then we can use another tool to actually inspect that. And the way we're going to do this is with a tool called GNU Radio. GNU is awesome. There's a lot of really cool stuff that you can do with it. You can do really complicated transmitting and demodulation for all sorts of signals. It's an open source product. It has a vertical learning curve, though. If you have used this before, you know it takes a little bit to understand how this works. And it's really just a front end for generating Python scripts. All it does is you put in your blocks, you connect everything, and then it's going to save the graph that you created as a series of Python files. And so you can then go and just run them as Python files, or hook them up to something else more interesting. And this is an example of a GNU graph, a more complicated one. We're going to do something much simpler today. But this is what kind of things can end up looking like once you get a little bit more knowledgeable on this stuff and start to interact with other types of blocks. And there's one more thing I want to talk about before we get to the capture portion of this. It is a note about Nyquist theorem and sample rate. So there's this theorem called Nyquist theorem that tells us that the sample rate of our signal must be twice the carrier frequency. And so, for example, our carrier frequency is about 430. That means our sample rate to get enough fidelity to understand what's going on should be at least about 1 billion samples a second, which is a lot. And this radio cannot do 1 billion samples a second. So you might be wondering, well, how are we going to do this? Fortunately, because we're doing ASK and we're just checking for the presence of a signal or not, we don't need that really high fidelity. But if we were analyzing some complicated QPSK signal where we needed to see the phase changes really in high definition, we wouldn't be able to do that with this radio, most likely, at this sample rate. And so you get the idea of sample rate here, right? If we increase the bit depth, we're capturing power points over time. If we get more power points over time, we get a cleaner signal, right? Cool. So back to demo. So we're going to open up GNU. Similar to GQRX, this is just, you can do it through apt install or you can grab it from GitHub. I believe you can do it from apt install, actually. It's been a second. There's guides for installing this stuff online. And this is what GNU looks like when you open it for the first time. So the first thing we're going to do is set our sample rate to 20 megasamples, which is the maximum this radio can do. And these are just Python files, so you can use standard floating point definitions for these numbers. So we can just do 20E6 for 20 megasamples a second. Hit apply, OK. And this is just a variable, so now we can reference this variable in any other block that we create. And we're going to go over here, Control F, Osmocom source for the radio. We'll double click on this. And it's going to transfer these numbers in floating point values. That's what the blue definition here and the output type defined here means. You can do this a couple different ways, right? You have like, for this, it looks like you only have one option. It depends. Sometimes you can do this in like binary values or other things. It depends on the source. And so for the frequency, this is going to be our carrier frequency, which 433, 639, I think. 433, 936. 6. All right. And then everything else should be fine. Hit apply and OK. And then we're going to use a waterfall chart just to verify that this is set up. So we'll drag in a waterfall chart, waterfall sync, and then we go output to input here. You'll notice it turns black to indicate that the errors were resolved of not having a connected source. And then here we want to set our carrier frequency as the center frequency. We could have done this through a variable as well, but 433, 936, E6. And we should be good to go. So now when I hit play, I have to save it. We'll do overwrite this file is fine. I had this issue in testing too. I'm going to open the chart I had before. Here we go. All right, so you'll see this is capturing data, same as the example we had before. When I press the lock button, I'm going to get a blip right there, so that verifies that we're capturing data. When I click X, it's going to stop capturing. And so right now I had this file sync created as well. The idea here would be this is just capturing and sending it to a data sync, like a visual sync. If we want to save that to our disk, we can use a file sync to record that to a file. And so you would just search that over here. I'll do it for you guys. So file sync, drag this on. We would connect this to this. Again, these are just Python files in the back end. Go in here, name the file, and we're good. I'm going to do this one more time to save the file properly. So the one thing about this is we're capturing a lot of data. We're capturing 20 million samples a second, and so these files are going to get very big very quickly. Even that file I just created was probably a few gigabytes. So I'm going to recapture this and just save like a second or two of data to make sure we don't have massive data to analyze later. So again, I'm going to play it, press the lock button, and stop it. OK. And then we can verify this on disk. So this one, I believe, was called jeepfob2.bin. So if I do a long listing, you'll see this was about 400 megs in that half a second or whatnot that we captured, or 1 second maybe. And we can verify this is just it's just data. you'll see we do have data. So it captured something. We don't know what it captured yet, but again, we have that. It's essentially like an audio recording from a microphone. And then we can go use other tools to analyze this. I'm going to jump back to the slides. There we go. All right, and so now we have that file. And we need to do some analysis, so some inspection on that data to try to find the bit stream that was sent and extract it from that broader recording. You could think of this as if you have that audio recording and you're trying to pull out somebody's voice specifically, right? So let's say you have a whole band playing, there's drums, there's horns, guitar, everything else. You just want to get the voice. And so we're going to figure out where that voice is in the data, in the broader data. And we're going to use a tool called Spectrum for this. This is, again, open source. You can install it using apt. I know this one you can install using apt specifically. And it's very simple. This is much simpler to use than GNU. We're going to put in the sample rate. We're going to use some filters. And we're essentially just using a series of sliders or faders, if you want to call them that, to select down onto the data. And then we're going to select the bit stream and use a symbol tracker to pull that out. And so right back to it. Go ahead and close GNU. All right. This will take a second to boot usually. All right, and so this is in Spectrum. We're going to open the capture that we have. So this was FOB 2. And then you can see we have a capture. And so this was already all the way open, but you want to make sure your power minimums and maximums are all the way open here. I like to start zoomed out. And then FFT size is kind of the height. So like this way, how big that wave is, or how big the display is. And you'll see we have some arbitrary data here. There's like some noise here and here and here. But if we start to scroll over, eventually we start to see what looks like data to some degree. Something's happening here. This, I can tell you from some experience, is just a synchronization. So the radio is sending a long pulse and then a series of alternating bits. And then the next thing will be data. So you can see here we have some shorter pulses, some longer points of 0. Over here is some longer points of 1. And so to start to get this data back, what I'm going to do is start to close in the filters. So I'm going to increase the power minimum, and you'll see we start to isolate this bit stream. And I can isolate from the top down as well. And then from here, I'm going to right-click, add a derived plot, and add an amplitude plot. And this will give us the selection window, and we can use this to now highlight the data that we're looking for. So we'll drag this down. And we want to line up that red line onto the carrier, which is this wave that we see in the center here, this sort of high power area. And then now we have this sort of external filter. You can think of this as like your minimums and maximums. So this will average out the data in that range, and it'll give you your minimums and maximums. And we're going to start to close this in. And then you'll see sometimes we don't really get coherent data here, and we have to modify our power faders as well here. It's possible also because of the noise of other radios at the conference that we're not going to get good data, so I may have to pull a capture, but I think we'll be okay. So here, this looks decent. I can tell you this is pretty noisy. It usually is a little bit cleaner than this. But this may be good enough. We can try. Let me see if I can get a little bit better isolation somehow. Let's try this. Okay. And then from here, we're going to right-click, add a threshold plot. And so now you'll see we have a threshold of this dotted line in the center. If it is above that or below that, we're going to get a sample here. And so if we were to zoom in on this a little bit, it's a little clearer, right? We have a leading edge and then a trailing edge here. I can try to highlight this a little bit better. This is decent. I'll show you guys after this. I'll show you a cleaner capture so we can see it a little bit more obvious. But this is going to be good enough, I can tell you. So we have ones and zeros, good enough. You can see like clean lines, clean vertical lines, a nice square wave. And then from here, we would go and extract the samples, but we need to first tell it what a symbol is. We need to tell it what it's measuring from where to where. And we do this by enabling cursors. So we select this, I'm going to drag it on here. And then from here, this would be 1 bit, right? We're telling it over at this point, measure based on the threshold plot, is this a 1 or a 0? And so here we can start to increase this. Let's go to like 5, and you can see now we kind of need to align things here. We will move over a little more. Let's go to like 50. And then I'll go all the way to the end of this transmission. And I'm going to set this to like 250, and then we'll go down until we kind of find it. All right, cool, 225. Let's call it like 230 just in case. All right, cool. So now we basically have it. You'll see this wasn't perfect, right? We have some misalignment here and there, but it should be good enough to give us a series of 1s and 0s. And then we're just going to right-click this, extract symbols, and then we'll go straight to standard out. If you go back to your terminal, you'll see that we've dumped those bits to the terminal, and we can grab those and now go and decode them. Before we go on, I had a feeling this might happen here, just because we are there's a lot going on here, right? There's lots of signals around us. That I have a capture that's probably a little bit better. I'm going to grab this FOB1 capture and show you what like a little bit cleaner signal would look like. So let's find that bit stream somewhere in here. Yeah, right around. Let me zoom out. That looks good enough. And then, so this is obviously a little bit cleaner. We'll zoom in on these, and then I'm going to adjust my power down. Right, you can see this wave is a little bit more, like the edges are better defined. And then from here, these are going to align a lot better. So if I was to enable cursors here, I'll just enable 1. And then we'll line up the edge. We'll do like 10. Make sure it's aligned. Do like 50. Line it again. And then we'll go out to like 250 all the way to the end. Just make sure this is aligned. Right, and so we would go ahead and dump this. So you can see the difference between these two is that the symbol lines typically are falling more aligned with what we captured. This could be a product of noise. Maybe I didn't get a good capture with the radio. You can try different distances from the antenna as well. If you're too close, that can cause issues, or if you're too far away, right? So you just play around this until you get a good capture, and then you should be able to get those bits back. But I'll leave this open here. This will be important for the next step. And I'm going to just go back. I think I have like 1 slide for this. So let's go out here. So the last portion is we want to decode this data. And there's a couple things that are kind of gotchas here. So you would be thinking like, well, we have the bits. That's just the data, right? Like, we're done. Unfortunately, there's one more step. So our goal here is to get the coherent data back. We don't care about just having a bit stream. We want to have the actual data. And this isn't just arbitrary, bits. Like it means something, and it was encoded specifically a certain way. So this happens for traditional data mediums as well, like Ethernet and Wi-Fi. Or I guess Wi-Fi is what we're talking about here, but Ethernet would be another example of this. And specifically, we're talking about an encoding type called Manchester encoding. And importantly, what this does is it ensures that we don't have more than 2 bits of the same type, so 2 1s or 2 0s in a row before we transition and have a state change. So we could have 1 1 and then 1 0, but we're never going to have more than 2. And this is a synchronization thing, so it ensures that the data that's coming through is reliable. And because we're transmitting data through the air, you saw we have like weird edges sometimes, but if we have more state changes, it gives us more things to analyze or more things to see. And this is the same perspective for the radio. Right, I'm sure there's a much more technical example for this, but at a principle level, that's what's going on. There's other types of encoding. There's non-return to zero is another common one. But Manchester is the one that is in use on this wave. And it's actually what was used for the original 10BASE-T Ethernet standard. Now they use a different encoding that allows a little bit more bandwidth. Because keep in mind, like this is going to increase the number of bits we need to represent that same data, source data. And so certain encodings are more efficient. And there's certain requirements for reliability in certain settings and things like that. But this is a modern key fob. Again, this is the key fob that's being used on Chrysler vehicles coming off the lot today. And so Manchester encoding is still very relevant in modern technology. And so right back to the VM, let me show you what that looks like. So we're going to copy these bits. We're on standard out. You could have just copied these directly to keyboard from Inspectrum. And then we're going to open Firefox. And I'm going to go up to, let's just start with CyberChef. I don't have a signal. Do I have them here? I do not. Well, let's see. Fun with live demos. Let me try. All right, I may have to revert to our recording here for this, some sort of network issue. If I was better at Linux, maybe this wouldn't be an issue. All right, so let's just go through the video here. That's okay. The idea is that we are going to take these bits. We're going to copy them, and we're going to go bring them into CyberChef. The goal here is we just need to strip out those commas and spaces. And so we want to have a series of ones and zeros with no other noise here. So you'll see I'm going to paste these in. I'll just replace the commas and spaces to clean this up. And then I'm going to look for a Manchester decoder. There's a variety of these. Decode.fr is fine for what we're doing. We'll take that bit stream, we'll paste it in here. This is the Manchester encoded bit stream, and we'll use line decoding. You'll notice we get a few question marks at the end there. And the reason for this is that we need to have a certain amount of data to represent a full amount of source data in a Manchester bit stream, right? And so if it can't figure out that full amount of data to figure out the source data, then it's going to fail. And so this is our bit stream, decoded, Manchester decoded now, so the source data. And we can go from binary to hex to represent this as hex. And then I'm just going to briefly talk about what the bytes mean. So now we have our source bytes that were transmitted. And the first 4 bytes here are going to be the ID of the key fob. So different fobs will have different IDs. And these bits represent the specific unique identifier for the key fob. And so when you go to the dealership and you get a new key fob, right, they will take that code and they'll whitelist it in your vehicle's computer so that it knows that that key fob is associated with your vehicle, right? The next 4 bits, let me get those highlighted here. These are going to be the command code. And this is specific to this key fob, of course. Different key fobs might use different codes. But in this case, this is going to be your command. So this could be an unlock. You're trying to lock the vehicle. You're trying to set off the panic alarm. Maybe you have a trunk that you can open with a button, something like that, or a vehicle remote start. And that's the next 4. And then the last 6 here are going to be something called a rolling code. So most modern key fobs have this idea of a rolling code where there's a unique value that is determined by a pseudo-random number generator with a specific seed and a, cryptographic, sort of either it's a chip on the device or there's something in software that does this that generates a unique random code that's predictable. It's kind of like your 2-factor auth with Duo or something on your phone. And this is known between the vehicle and the key fob, and it's used to ensure that me, Hacker Nate, can't go and generate arbitrary commands to unlock the vehicle, right, and steal your stuff. And so this has been pretty common for the last, I would say, between 10 and 15 years. You will see a variety of key fobs between like 2010 and 2015 that don't use a rolling code. And then before 2010, it's very common that they didn't use one at all. Rolling codes are still susceptible to something. I'm going to talk about an attack that still works on this vehicle, and you can go home and probably do to your own cars. It is called a roll jam attack, and this was popularized by Sammy Kamkar back in 2016, and it's still not been patched. So the idea of a roll jam attack is that we have a rolling code, right? And so anything that's been consumed cannot be used, right? So if I press my unlock code and it hasn't been used, the vehicle says, okay, this is a valid code, I'm gonna let you unlock the vehicle. But if I try to replay that signal, it says this code has already been consumed, I can't use that code anymore, I need to generate a new one. And so what roll jam does is it jams the carrier frequency of the key fob, and the user will press, it knows the power level that it's generating, right, in the jam. So it will capture the signal, you press the key, and it doesn't unlock the vehicle because it's jammed. You press the key again, it doesn't unlock it because it's jammed. Now the roll jam device stops jamming and only replays the first code. And now it still has the second code, but it hasn't been consumed yet. And so the user is going to have to press the key twice, but we're all kind of monkeys. We'll just press the key twice, and it's like, okay, it messed up the first time, but it worked. And then now we have this valid code as the hacker. So what you can do is you can build this device for like $40 and stick it under the car with a magnet, and it will always have the next available code. And then as soon as the vehicle parks, the person gets out, goes inside their house, you take the device off the car, you press the button on the device, unlocks the car, and you steal the stuff, right? The way that you would fix this is you would need a negotiation between the device and the car similar to two-factor authentication, where you're verifying that this is a real-time authentication. And so this is possible. Like the key fobs can do this. Funny enough, the prox lock on these cars, like if you stick your hand in the door handle, the car reaches out to the key fob. The key fob responds with an authentication code. It's FSK actually, it's not ASK. But it has a negotiation capability. They just haven't set it up for the ASK property for remote unlock. And so they can mitigate this today, theoretically in software. There's theoretically a patch that works for this. I think the manufacturers either just don't care or they don't think this is real world or real effect. But I promise you this works. There are plenty of videos on YouTube of people using roll jam to unlock vehicles and do all sorts of fun stuff. And you could definitely build this at home, again, for about $40. And play around with this yourself. So with that said, that's pretty much it for today. I'm going to give you these references, and if you want to, again, come up, check out the key fobs that I brought. I'm happy to give those away. I have a variety of key fobs, first come, first serve. These references are great. I do want to point out a couple things. So the first link here is Sammy Kamkar's video. I want to attribute a major thank you to him and that previous work. I think that's basically what got me interested in this stuff and help me get started here. He talks a lot about a garage door opener that he hacked and some other stuff, and then that's the video where he announced the roll jam at a conference in the first place. The second one is Michael Osman's HackerF resource, so you can see more GNU radio graphs and things like that. The third one is the FCC ID page, so where you can search for the things for where we were searching for carrier waves. And then the last one is an instructional guide on how you can build your own roll jam today and go play with that. So with that, thank you, and I will take any questions. If there are any questions, we can get people up here to check out the hardware. Thank you. All righty, folks, thank you.